Hello everyone, I'm Mr. Lee. Welcome back to Mr. Lee's Math Class videos. We're in the middle of section 7.4, part 1. We are going to finish up double angle identities and then talk through the other half of 7.4, which is half angle identities as well. So simplify these expressions down below. Again, sometimes, as we talked about with the double angle identities before, if you have the right side of something, you can convert it to the left. I'm going to leave A for you to practice because it's similar to what we've done before, but I do think I want to talk about B. Sometimes things don't look like exactly the form you might be used to them being in. For example, if you look on our original notes from previously, we don't have a 1/4 minus 1/2 sine squared A, but we do have something that looks similar in the 1 minus 2 sine squared A. So if I factor out a fourth, which is really dividing everything by a fourth, I'll have 1 minus 2 times the sine squared of 47.1 degrees. And then suddenly this piece right here does look like 1 minus 2 sine squared A, which will allow me to convert into cosine of 2A. In this case, the A is 47.1 degrees. And so this is equal to 1/4 times the cosine of doubling 47.1 should be 94.2 degrees. So you can clean it up into a much more simplified form. But that's really the main part of these double angle identities. One thing to take note of is that you have seen sum and difference identities, and you now have a double angle identity. What this actually allows you to do is you'll see things like sine of 3 theta or sine of 3x or cosine of 3 theta or 3x, and you can then break them down into x plus 2x and then use a combination of the double angle identities and the sum and difference identities to figure out what those end up being. Now, for the second part of 7.4, we have half angle identities. So the half angle identities are very similar to the double angle identities, just solved for the piece that's by itself. In particular, because cosine of 2A has multiple things that it's equal to, one of them is 1 minus 2 sine squared A. So what we can do is substitute or get the sine squared x by itself by moving the 2 over and the cosine of 2x over, dividing by 2, and taking the square root. And then again, if from one perspective you are doubling, going from one side to the other, inherently from the other perspective you are halving the angle. So it's just repurposing the visual direction and then making a substitution and saying, well, if we call this 2x and x, to distinguish the fact that this is a half angle identity, we can set 2x equal to a, and that way x will be equal to a over 2, and it will appear to be a half angle identity. This one has a plus or minus because it kind of depends on whether or not what quadrant you're in as to what sign that will take. Because that cosine of 2a has another equivalent of the 2 cosine squared a minus 1, it produces a very similar outcome when you're solving for cosine in that situation using an alternate version of that double angle formula. So you'll see that the sine of a over 2 and cosine of a over 2 are very similar. The only difference is on the inside. You have a minus and a plus. And then to derive tangents, if you have sine and you have cosine, you can just divide them because they both have over 2, so those will cancel. So you end up with a 1 minus cosine a over 1 plus cosine a. And if you multiply by different conjugates, you can either end up with a numerator that's only one term or a denominator that's only one term. I think you can make an argument for this one because it only uses cosine A. But I think this one is the best down here because it has a denominator that's only one term, which allows you to do things like split pieces or bring pieces together in a different way than when the numerator is that way or when there's a square root already in there. So this is the one that I actually like the most because if you already have cosine A, it's very easy to draw the triangle and get sine A. So what is this going to look like? We can now calculate some of these things, which we've done before, in different ways than we were doing it before. I'm going to do A and B And I'll leave you to try C and D so you can get practice using the tangent one. So the cosine of 15 degrees is really the cosine of 30 degrees divided by 2. So when you're going left to right on this equation, you're going to take the angle, if you have just a cosine or sine, and write it as something divided by 2. Effectively, the numerator is only going to be double what the original angle is, because that's what divided by 2 means. But this tells you that your A is actually 30 degrees, in this case, in the formula that's here to the right. So we know that the cosine of A over 2 is 1. It's the square root of 1 plus cosine A over 2. In this case, the A is 30. So the square root of 1 plus the cosine of 30 degrees over 2. Now we know what the cosine of 30 degrees is. It's 1 plus root 3 over 2 over 2. If you rationalize or you multiply by 2 over 2, here that it can clear this denominator. This is the square root of 2 plus square root of 3 over 4. Or the square root of 2 plus square root of 3 all over 2, because the square root of 4 is 2. So this is what the cosine of 15 degrees tends to boil down to when you are doing this way. Now, of course, there's always the plus or minus in front, but because these are both first quadrant, we know it's going to be positive. So you can, if you already know what quadrant you're going to be in, you can kind of already tell if it's going to be positive or negative. Most of them done this way that produce 15-degree angles. It'll be either 2 plus or 2 minus under the square root, and there could be a plus or minus out here, so that'll give you the 4 general options.